this is the 40th lecture, and the topic today would be more on positive real functions and their synthesis. Yesterday we had opened this topic on testing of positive real functions, and we saw that testing requires first to test whether f of s is real for s real. This is an obvious inspection test. You can conclude by looking at the function. Second is that you do a Hurwitz test on the denominator. If f of s is n of s by d of s, then you test whether d of s has any roots in the right half plane. So poles, no poles in RHP, open or closed? Open. Open, because poles on the j omega axis are permitted. If you discover poles on the j omega axis, they must be simple poles on j omega axis with real positive residue, and if it satisfies all the three, then the fourth one would be the test of the real part of capital F on the j omega axis. Real part on the j omega axis, you have to find out whether this is true or not for all omega. And we saw the mechanization. Mechanization is, this is by inspection, this is obtained by Hurwitz test on d of s, and if there are poles on the j omega axis, they will be revealed in the Hurwitz test. So you find whether, how, it is the last divisor which will reveal if there are poles on the j omega axis, and then test whether these poles are simple or not, and if they are simple, if they are multiple, then you do not go further. If they are simple, then you test their residues and find out whether they are real and positive or not, and finally if all of them are satisfied, then you go to the last one. And the last one, as you saw, we had simplified into the following: if f of s is equal to m1 plus n1 divided by m2 plus n2, then all that you have to test is a polynomial a polynomial which is a of x, which is equal to m1 m2 minus n1 n2 under the condition s squared equal to minus x. You have to test whether this is non-negative for x is omega squared, so omega negative as well as positive are taken care of. So it suffices to do for x greater than or equal to 0. Okay, this is what the fourth test is all about. And with this, we had considered one simple example of a linear polynomial divided by a quadratic polynomial. Today we consider a biquadratic polynomial, that is a quadratic divided by another quadratic. And you know that all such functions can be written in this form, s squared plus b1s plus b0, and you can have a multiplying constant k. We can write the numerator with leading coefficient equal to 1, denominator with leading coefficient equal to 1. Then obviously the first criterion would be that k a1 a0 b1 b0 must be greater than equal to 0. They must be real, all of them must be real, and they must be greater than or equal to 0, with one exception. What is the exception? What is the exception? K cannot be equal to 0. If k is 0, it is a trivial, isn't it? So k has to be strictly greater than 0. K cannot be equal to 0. Alright? That is a trivial thing. Alright, that is the first thing. Now therefore we can forget about k. We can simply concentrate on the rest of it. If you want, you can call it an f1 or f prime or whatever it is, or you normalize k to 1, because k is of no concern. Okay, k has to be a real positive quantity. So let us consider this biquadratic, s square plus b1s plus b0. The second thing, second test says that you carry out Hurwitz test on the denominator. Obviously if b1 and b0 are real and positive, there is no need. The real part of the roots shall be negative. Okay, but there is one the third one says, are there poles on the j omega axis? Well, if there are poles on the j omega axis, obviously you require B1 equal to 0, isn't that right? If there have to be poles on the j omega axis, poles on j omega axis, and under that condition, what would be the the pole obviously is simple. Okay, we have s squared plus b naught, and therefore the roots are at plus minus j square root of b naught. They are obviously simple. You have to test the residue. Now, is the residue half a1? Whether it is or not, I think I left that as a question because it's a fuzzy decision. If b1 is 0, you will see that for the function to be positive real, there are constraints on the other constants. Let us see what these constraints are. So, this point, whether the poles whether the residues on the j omega axis are real and positive or not, we leave it for the present. We skip this to the fourth test, that is, we find out what is a of x. A of x obviously is m1 would be a0 minus x, alright, m2 would be b0 minus x. Is this step clear? Why it is a0 minus x and b0 minus x, and minus a1 b1 s squared with s squared equal to minus x, so it would be plus a1 b1 x. Is that okay? Plus a1 b1 x. So what I have to test is whether this is non-negative. Is this non-negative for x non-negative? Okay. Now, the right hand side can be written as x squared minus x plus a naught b naught, that is the constant term, and the coefficient of x would be a1 b1 minus a naught minus b naught. Is it okay? All right. Agreed? All right. So, we repeat this here. A of x equal to x squared plus a naught b naught plus x a1 b1 minus a naught minus b naught. I have to test whether this is non-negative or not. Now, I do a very simple thing. I have x squared and I view a naught b naught as square root a naught b naught whole squared. That is, what I want to do is to write this as x minus square root a naught b naught whole squared. Okay. Then I have to add plus twice square root a naught b naught x. Isn't that right? What I have done is I have taken minus twice square root a naught b naught x here and I have added it. So, there should be no change. Plus x into a1 b1 minus a naught minus b naught, which means that this is equal to x minus square root a naught b naught whole squared plus x into a1 b1 minus root a naught plus or minus minus, because when this comes inside it is plus, so square root a naught minus square root b naught whole squared. Agreed? And under what condition will this be non-negative? You see, a square term cannot be negative. So, the minimum value of this is 0. A of x should be non-negative even under that condition, which means that the coefficient of x here must be non-negative. That is, the condition is that a1 b1 should be greater than or equal to square root a naught minus square root b naught whole squared. Agreed? This is the condition on the coefficients. This is the restriction on the coefficient. All right. Let me repeat. A1 b1 should be greater than or equal to square root a naught minus square root b naught whole squared. Now, we had asked a question in the third part of the test, that is, under the condition if b1 equals to 0, if B1 equals to 0, then only we have poles on the j omega axis, right? Then the denominator becomes s squared plus b naught, numerator becomes s squared plus a1s plus a naught. This is my f of s if B1 is 0. Now if B1 is 0 and this condition is to be satisfied, A0 must be equal to B0. Therefore, A0 equal to B0, which means that our function now becomes s squared plus a1s plus b0 divided by s squared plus b0. Do you understand this? Is it okay? If B1 is 0, left hand side is 0. Now 0 has to be greater than equal to this whole square, and therefore the only condition is that the two sides must be equal, because right hand side cannot be negative. 0 is of course greater than a negative quantity, but the right hand side being a whole square cannot be negative, and therefore the only condition under which it is satisfied is that a naught should be equal to b naught. In other words, my function becomes this, which obviously I can write as 1 plus a1s divided by s square plus b naught. And now I am in a condition to state what the residue is. The residue is obviously half a1. Okay? Alright. And therefore we have found out the conditions that a general biquadratic, that is s squared plus a1s plus a0 divided by s squared plus b1s plus b0 is PR if and only if just two conditions are necessary. What are they? Number one, a1, a0, b1, b0 should be real and greater than equal to 0. Alright. Number two, just one more condition, that is a1, b1 should be greater than equal to square root a naught minus square root b naught whole square. I don't have to state the third condition, because the third condition, that is if b1 equal to 0, then a0 has to be equal to b0. This is contained in this. Just two conditions. Okay. Let's take some examples. Let's say s squared plus 2s plus 25 divided by s squared plus 5s plus 16 f of s. Is this PR? All that you have to test is a1 b1, which is 10. Is it greater than equal to, with a question mark?
Yes, sir.
Square root?
Yes, sir. 5 minus 1.
Okay, so it is 1. Now therefore it is PR. We remove this question mark sign. Suppose these two are interchanged. That is, instead of 25 I have 16 here and this is 25. Does it change? No. Therefore a0 and b0 can be interchanged. In this function, whether it is s squared plus a1s plus b0 or s squared plus b1s plus a0, it doesn't matter. But of course,
in every function it doesn't matter.
In every biquadratic,
Yes.
Not in every
Yes,
other
in
function.
every
Biquadratic. But the synthesis, that is the network realizing this, shall of course be different. If the constant in the numerator is taken to the denominator and vice versa, obviously the network shall be different, but the function shall remain positive real. Okay, what about if this no, okay, that's one. Let's take another function, 3s square plus 5 divided by s times s square plus 1 f of s. Now, how do you test whether this is positive real or not? Do I have to? Yeah, okay, I'll do that. I'll do that. I have to check the residue. You see, the poles are, one is at the origin and the other is a pair on the j omega axis. So what I have to do is to write this as k0 by s plus twice k1s. Okay, I can replace 2k1 by k1. How does it matter? Okay, so let's write it as k1s by s square plus 1. Can you say what k0 is? 3 or 5? K0 is 5. And K1 is minus?
-2.
I don't care it is -2 or -5. The sound minus is good enough for me. Okay? K1 is less than 0, so the function is not pure. Okay? The actual value is not important.
So you can see that initially the denominator is not a Hurwitz polynomial.
Denominator is not a Hurwitz polynomial. Why not?
So two terms are missing.
S cube plus
Oh,
S.
sorry.
It's a purely odd. It is a Hurwitz polynomial. Okay. Do I have to test the real part? No. Because it has failed in between. But suppose I had to. Suppose I had to. What is the real part of this? What is A of x? Identically equal to 0. Why? Because it's an odd rational function. Okay. Then some more examples. Let's say we have two positive real functions f1 and f2. You know that f1 plus f2 is PR. Okay. F1, F2 not necessarily PR, may or may not. F1 minus F2 belongs to the same category. F1 by F2 belongs to the same category, not necessarily PR. What can you say about F1, F2 divided by F1 plus F2? It is PR because it can be written as 1 over F1 plus 1 over F2. PR plus PR. So the total thing is PR and 1 by PR is also PR. Okay. Alright. Now let's take some specific examples of this. Let us say you have K divided by S plus alpha. Is this PR? K and alpha are real and positive. Is this PR? Yes or no?
Yes, sir.
I can write this as S by K plus alpha by K. This is PR, this is PR. PR plus PR is PR, 1 by PR is PR.
But isn't it division of 2 PR?
Pardon me?
So isn't it a division of 2 positive real functions?
Division of two positive real functions, but this is division of two positive real functions is not necessarily PR, but in this case it is PR. You should view it like this instead of a division of two positive real functions. Suppose I multiply this by S. Is this also PR?
Yes, sir.
Yes, of course, because I can write this as 1 over K plus alpha by Ks. This is also PR. Okay. Next, suppose we have S plus alpha divided by S plus beta, where alpha and beta are real and positive. Is this PR?
Yes, sir.
Yes, of course, because I can write this as S by S plus beta plus alpha divided by S plus beta. So this is also PR. All right. These are some of the elementary functions which are PR. Now let's look at. We had done yesterday some problems on synthesis, some very simple problems. Let's look at the general principles of synthesis of a driving point function. By this we mean either an impedance or an admittance, a driving point emittance. And to be specific, let's say we consider impedance. For example, if the impedance is, let's say, K by S plus alpha, then what we do is, we could do it like this. We could write this as 1 over S by K plus alpha by K. This is admittance. Therefore, Y of S is equal to S by K plus alpha by K, which means that it is a parallel combination of a capacitor and a resistor. The value of the capacitor is 1 by K or K? 1 by K, alright. Then the resistor K by alpha. Do not make a mistake. We never write conductance value, we write resistance value. This is a conductance, so the resistance is K by alpha. Alright. If this was, let us say, Ks by S plus alpha, if that was my Z of S, then I write this as once again 1 over 1 by K plus alpha by Ks, and therefore the admittance is 1 over K plus alpha by Ks, which means that I have a resistance in parallel with inductor, and the value of the inductor is alright, and the resistance is not 1 by K, alright, do not make a mistake. This is the convention that we follow, that element values are resistance, capacitance and inductance, not their reciprocals. Okay. The general principle appears to be, even in these trivial cases, that you express the given function as sum of simpler functions. Well, in this case I could not express Z of S as sum of simpler functions. So what I did was I took Y of S, its reciprocal, and expressed this as sum of two functions, each of which I could synthesize. Similarly, here also what I did was I found out the admittance could be decomposed into a sum of simpler functions. The general principle in driving point function synthesis is, if possible, decompose Z of S into a sum of simpler functions ZIS summed over I. If not possible, then take the admittance and decompose that into simpler functions. Okay? It is one of the two, either you work with the impedance or the admittance. Now in between, after you do that, you might find that one of these components can be decomposed when you take its admittance. So you do that and you go on doing this till you get elementary elements, namely resistance, capacitance and inductance. That is the principle, general principle. It does not always work because you may not be able to decompose. Let us take some examples. Suppose Z of S is equal to, let us say, a m s to the m plus a m minus 1 s to the m minus 1 plus etc. plus a 0 divided by b n s to the n plus b n minus 1 s to the n minus 1 plus etc. plus b 0. Suppose this is your function. Now we know that m could be equal to n, or m could be 1 greater than n, or m could be 1 less than n, right. This is the difference, this is the restrictions on m, that m must be, the restriction is m must be less than or equal to n. Is this correct?
Yes.
No. I write a wrong thing and you all agree. Can m be 0, for example, and n can be 3? Can that be true? The powers,
So difference should be less than equal to 0.
difference is either 0 or 1. Period. It cannot be more than 1, and therefore m, the possibilities are m can be equal to n, can be n plus 1 or n minus 1. That is it. One of them. Alright. Suppose suppose to be specific, suppose m is equal to n plus 1. Suppose let m be equal to n plus 1. Then the function Z of S will have a pole at infinity. Isn't that right? If the numerator degree is 1 greater than the denominator degree, then obviously as S tends to infinity, the function tends to infinity. And this pole is on the j omega axis, it is a simple pole, and the function shall qualify for further PR testing if the residue at this pole is real and positive. What is the residue at this pole at infinity? Can you tell me by inspection? It is simply am by bn, and therefore I can write Z of S as equal to am by bn s plus the rest of the function Z1 of S. the step that we have done is called pole removal at infinity. Obviously, that is what we have done, and since all coefficients are to be real and positive, obviously am by Bn, that is the residue at infinity, is also real and positive. Okay. So, this is PR. Now, Z of S is PR, Z of S is PR, this is PR.
So how we get the residue as n by b?
Oh, we allow S to go to infinity, only the highest powers count, only the highest powers count, and therefore we get
n is equal to n plus 1.
M is, that is what we assume, M is equal to n plus 1. So, as S tends to infinity, Z of S, S tends to infinity, this tends to Am by Bn times S.
Yes.
The rest of the terms do not matter. What is the problem? Okay, suppose we had, let us say, S cubed plus etc. divided by half S squared plus etc. At infinity, obviously this behaves as twice S, and therefore 2 is the residue. This residue is obvious by inspection. A big question now is the remainder function Z1 of S, which is a difference between two positive real functions, is not necessarily PR. Okay, let us see whether it is PR or not. Let us see. It is not necessarily PR, it could be PR also. Now, what are the conditions for positive realness? If S is real, Z1 of S should be real. This obviously must be true because Z of S is PR. Therefore, when S is real, Z of S should be real, which is obviously true. This is real, this must also be real. Sum of a real and a complex quantity cannot be real. Alright? Okay. So, first condition is satisfied. Second condition, does it have, can it have poles in the right half plane? Can Z1 of S have poles in the right half plane? Obviously not, because if it has poles in the right half plane, the same pole shall belong to Z of S also, but Z of S by hypothesis is PR. Therefore, Z1 cannot have a pole in the right half plane. Next, can it have a pole on the j omega axis? Yes, it can, but can any of these poles be multiple? No, because that pole also belongs to Z of S. By the same token, the residue at a simple pole is obliged to be real and positive, because that residue also belongs to a positive real function Z of S. All that remains for us to test is the real part of Z1 of j omega, whether it is non-negative for all omega. Well, don't you see that the real part of this term is 0? For S equal to j omega, this term is purely imaginary, and therefore real part of j omega, Z1 of j omega is the same as real part of Z of j omega, and this has to be non-negative for all omega. Therefore, Z1 of S is PR. Agreed? Can I explain? Okay. The problem was that we are removing a positive real function from a positive real function. Is the remainder positive real? That was the question. And we have shown by systematic argument that Z1 of S, the remainder function, has to be PR. There were three arguments. One was that if S is real, it has to be real. If it is complex, then Z of S will not be PR. If it is a pole in the right half plane, that pole should also belong to Z of S, so it cannot have a pole. If it is a multiple pole on the j omega axis, that also belongs to Z of S, so it cannot have a multiple pole. The residue at a simple pole has to be real and positive, because it is also a residue of Z of S. And finally, the real part of Z1 of j omega, because Z1 is Z minus Am by Bn S. And if you put S equal to j omega, this term becomes purely imaginary. So, the two real parts are exactly equal, and real part of Z of j omega is non-negative. So, real part of Z1 of j omega is also non-negative. In other words, what we have proved is by removing a pole at infinity, you do not destroy the positive real character of the remainder function. In other words, what you have got is a partial synthesis of Z of S, that is, you have got an inductance of value Am by Bn and the rest of the function is Z1. Rest of the function is Z1. Then you can look at Z1. Okay? Partly it has been synthesized, the pole at infinity has been removed, then you look at Z1. Does Z1 have a pole at, can Z1 have a pole at infinity? No, because pole at infinity has already been removed. So possibly Y1 may have a pole at infinity. In other words, Z1 may have a 0 at infinity, then Y1 shall have a pole at infinity, and perhaps by taking the reciprocal you may be able to remove that pole.
So Y1 also can't have, because now the orders of the denominator and numerator are the same.
No, it is not necessary. By removing the pole at infinity you don't equalize the order, you don't necessarily equalize the order.
Here M is equal to M plus 1.
Oh, doesn't matter. You might cancel more than 2 terms, more than 1 term. It's possible. We will show examples. All right.
So this is not clear how we can cancel terms.
How we can?
So when we removed S,
Yeah.
when we removed a pole at infinity, then why the degrees are not equal?
Why the degrees are not equal? Suppose the degrees were unequal to start with. They were unequal.
Yes, sir.
Okay. Suppose we had an odd polynomial s cube plus etc. divided by an even polynomial.
Yes, sir.
If you remove the pole at infinity, you are still left with a difference of 1 in their degrees. Okay. Suppose n of s by d of s, suppose this is of degree 3 and this is of degree 2. By removing the pole at infinity, you will be left with a polynomial whose numerator shall be either even or odd and the denominator shall be the opposite. We will take examples. Okay, we will be convinced when you take examples. The degrees are not necessarily the same. Yes.
Then how we rule out the possibility of having a pole at infinity?
Oh, because
Because the original function have a simple one.
because Z of S had a pole at infinity which has been completely removed. If Z1 of S also has a pole at infinity, this must be added to this. We have removed the pole at infinity from Z of S. So the remainder function cannot have a pole at infinity. No? Okay, let's take an example. Suppose we have s cube plus 3s divided by s square plus 1. This has a pole at infinity and the pole at infinity has a residue 1. So it is s plus the remainder. Now what do you think the remainder would be? The denominator is s plus 1 and this would be 2s. So the degrees are not necessarily equal. Degrees are not necessarily equal, number 1. And this function does not have a pole at infinity, cannot have a pole at infinity because we have removed this pole. If the remainder also has a pole at infinity, that means we have not been able to calculate the residue properly. Or you can argue like this, I will take half s here and the other half s I will add with this. But what's the fun? If the remainder function is equally complex as the original one, you have not made any progress. So you don't remove partially, you remove completely. You remove pole at infinity from this and talk about the remainder function. Okay? Alright. So what we have done is Z of s we have said, now let's denote the residue at infinity as k infinity plus Z1 of s. K infinity we are making a symbol, instead of am by bn I am writing k infinity. Now let us go back to the original function. Original function was a m s to the m plus etc. plus a0 divided by bn s to the n plus etc. plus let us say b1s. Suppose the b0 term is not there. The lowest powers cannot differ by more than unity. that is lowest powers could be equal if B0 was there, lowest power could differ by 1, that is the denominator could have a power of 1, the numerator has 0 power, alright, or it could be the other way around, we may have missed A0 and B0 is there. I am taking one specific case. Is there a problem? Why don't you put a piece of cloth? There is some problem. Okay. Yadavji, you can go ahead with the recording. Okay. Recording is okay. Now, if that is the case, is this a permissible thing? Does this necessarily make Z of S non-PR? No. We can have a degree difference over. If this is the case, then what can you say about Z of S? Its behavior at origin, at S equal to 0. It has a pole at the origin, which means that I can write this as K0 by S plus some other function, let us say Z2 of S. Agree? So, if you discover that there is a pole at the origin, you can remove this. Now, what is K0? K0 is obvious by inspection, it would be A0 by B1, A0 by B1, agreed? So, and then by the same arguments that we did in this case, we find that Z2S is also PR by the same arguments. Z2S is also PR. In other words, what we have obtained is, we have obtained a partial synthesis, this a capacitor of value 1 upon K naught. Yes? No, we have not assumed anything. M and N could be equal. This is not of importance. The relative degree difference, whether M is equal to N or N plus 1 or N minus 1, does not matter. What we are saying is the behavior at the origin, that is when S goes to 0, all other terms disappear from this thing. It is only S equal to 0.
The pole at infinity, no other poles.
No, we are not considering whether the function has a pole at infinity or not.
Only the pole at 0.
Pole at the origin, and that is what we are removing. So, the rest of the function is Z2. This is also a partial synthesis. So, we can remove a pole at infinity, we can remove a pole at the origin, we can also remove a pole on the j omega axis. If we have a pole on the j omega axis, that is, we find that Z of S is N of S divided by S squared plus omega naught squared multiplied by, let us say, D1 of S. Suppose we discover that there is indeed such a factor. Well, what we can do is, we can write this as K0 S divided by S squared plus omega naught squared plus some other function, let us say Z3 of S, alright, where the residue at this pole is how much? K0 by 2. We should have written twice K0, but we are saying twice K0 is K0.
Here also we are assuming the same thing, that the other term is 0, K0S plus K2, and K2 comes out to be 0.
That is correct, it has to be like that, otherwise the function will be non-PR, isn't it? We have said that the residue is real and positive. So, what all we are doing is, we are adding a term like this to a term like S minus j omega naught, and this is exactly this. That is a condition imposed by positive realness character of the function. And by the same token, by the same arguments, they say this is an odd function. So, on the j omega axis it is purely imaginary. So, it does not contribute to real part. The two real parts shall be the same, and other poles arguments is the same. In other words, Z3S is also PR, which means that what we have been able to achieve is that we have been able to remove an inductance and a capacitor in parallel, and the rest of the impedance is Z3. Can you tell me what these values are? The inductance, for the capacitance 1 by K naught, is that correct? Okay, and then this one K naught by omega naught square. Wonderful. So, we have removed a series, we have removed in series a parallel resonance circuit. Okay. These are the various steps that one can employ. If one discovers that the function, given function, has a pole at the origin, remove it. If it is a pole at infinity, remove it. If it is a pole on the j omega axis, a pair of poles, remove it. All right. Now you can do this either with impedance or with admittance. If we had removed from admittance a term like this, that would have meant that we have removed a series resonance circuit in parallel. Agreed? If this was instead of z, if it was y, if this was y and this was also y, then instead of a series connection, we would have a shunt connection, a parallel connection of an inductance and a capacitor in series. Okay. These things would be illustrated with examples. I would not go into the theory because the theory is exactly the same. The fourth step, these are three steps of pole removal: pole at origin, pole at infinity, pole on the j omega axis.
So you do it in this order?
Not necessarily. You can do it in any order, and that adds variety and spice to life, because every time you get a different network, and then you choose. If you have a multiplicity of realizations, you choose which one according to your choice. Okay. You may like the shunted one or you may like the series one for different reasons. Okay. The fourth step that can be done is to look at this. We have already illustrated yesterday with an example, is to look at the real part of z of j omega. It has to be non-negative for all omega, and it suffices to look at in the first quadrant, right. It suffices to look at, because real part of z of j omega is an even function. It contains a numerator and denominator which contain only even powers of omega. So it suffices to look at in the first quadrant, and suppose that this variation is something like this. Okay, it has maxima and minima. Then you look at the absolute minimum, that is the global minimum. This is the global minimum, and suppose this value is r naught. Okay, obviously from z of s, if you remove this resistance r naught, the remainder function, let us say z4 of s, will this be positive real? Will this remain positive real? Yes, it will, because the minimum value of the real part of z4 of j omega shall now be 0 instead of r naught. Okay. This is another step that can be performed. If you remove a constant from a given rational function, the rational function may simplify. Okay. This is the fourth step that one can perform.
What is the advantage? You get a resistance of.
Or you get a simpler function. The degrees are reduced. Okay. Like in synthesis, because in synthesis means you must remove something which simplifies the rest of the function. Then you are making progress, otherwise you are not making progress. Okay. Now let us take a number of examples to illustrate this. First we take, let us say, 6s cubed plus 3s squared plus 3s plus 1 divided by 6s cubed plus 3s. Suppose this is a z of s. Alright, the degrees are equal. It has a pole at the origin. There is no pole at infinity. It is a pole at the origin, we could remove this. But before that, an intelligent eye, intelligent pair of eyes, should discover that the denominator is contained in the numerator, which means that we could remove a constant of 1. There is no guarantee that by removing the constant 1, the rest of the function shall be PR. There is no guarantee. But let us do this. Let us do this and see if the rest of the function is PR, then we have made progress. You see, the rest of the function is 3s squared plus 1 divided by 6s cubed plus 3s. Okay, which, pardon me?
So if the rest of the function is not PR, then the realization of the ZS is not possible here.
Will not be possible.
So then
Not
it is
possible.
directly not possible from, yeah, right.
It will not be possible, provided 1 provided the constant that you remove is less than or equal to the minimum value of the real part, then the remainder function shall be pure. Okay. If 1 is greater than the minimum real z of j omega, then obviously the rest of the function will be non-pure. But let us look at it. I am not finding the minimum value of the real part formally. I am just saying that since the denominator is contained in the numerator, let us see what happens if I do this. So what I get is 3s square plus 1 divided by s, 3s multiplied by 2s squared plus 1. Agree? So the remainder function you see is purely odd, not imaginary. When in terms of s it is not imaginary. When we put s equal to j omega, the function will be imaginary, which means that real part of z of j omega is equal to 1 for all omega, because this is purely imaginary. Is that clear? And therefore we should be permitted to happily remove this 1 ohm resistance. Agreed? 1 ohm is the minimum value, also the maximum value. We can remove that. Now if I do that, our synthesis has made progress. Z of s is 1 ohm plus the rest of it, which is let me use a different color. Let me call this as Z1. Then Z1 of s is equal to 3s squared plus 1 divided by, I will write as 6s cube plus 3s, and I shall keep my life simple. What I will do is, I could have written 3s times 2s squared plus 1, then remove the pole at the origin. I could do that. There is a pole at the origin? Yes, I could do that, but I want to keep my life simple. I want to make as few calculations as possible. So what I do is, instead of, this is the variety, I could do that, I could also do something else. What I do is, I find the admittance. I find this much simpler than the rest. I find the admittance. The admittance is a pole at infinity, right? And the residue is obvious. Residue is 2. So it is 2s plus, let us say, y2. Agreed? Which means that I have removed a what? A capacitor. From an admittance you remove 2s, so the capacitor value is 2, and the rest of the admittance is y2. Let us see what y2 is. y2 is 6s cubed plus 3s divided by 3s squared plus 1 minus 2s, which is equal to 3s squared plus 1, 6s cubed plus 3s minus 2s times 3s squared plus 1, which means there is a cancellation of this term with this term. So it is simply equal to s divided by 3s squared plus 1. Agreed? Wait a second, before I do that, please do observe that when I remove the pole at infinity, the remainder function cannot have a pole at infinity because it has been removed. Okay. The remainder function in fact has a 0 at infinity. That is not always the case, but here it has a 0. Now I can look upon this as if the synthesis problem is over, isn't that right? Because I can write this as 1 by 3s plus 1 over s, which means that in the network a series inductance of value 3 and a capacitor of value 1. Why 1 upon 3? 3s plus 1 over s, so 3 plus 1, and the synthesis is complete. This is an RLC network. Is it okay? This is an RLC network. Now I also want you to notice that after the removal of that 1 ohm resistance, we had a very specific, a very special type of impedance, which was the numerator was purely even, the denominator was purely odd, and therefore the total rational function is odd, It could be the other way around also, that is, I could have an odd divided by even, and I will now show rigorously that when such a function is encountered, the synthesis is in terms of pure inductances and capacitances, no resistance in this structure, alright, no resistances. In other
It
words,
is obvious because the real part is 0 and it is purely imaginary.
real part is 0 on the j omega axis,
So when it is an odd function, it is purely imaginary, so it is.
real part is 0, okay. So,
Since it is purely imaginary, it has to be made with the synthesis is possible by inductance and reactance.
that's right, Amandeep is saying a very interesting thing. He says, since the real part is 0, if the real part is 0, okay, if real part of z of j omega is equal to 0, then the power absorbed by the network is 0 from a sinusoidal excitation, which means that there cannot be any resistance inside the network. Perfectly all right. In other words, the network must be LC. Can we prove that if the network is LC, then the driving point impedance must be purely odd? Can you prove it the other way around? Yes, we can. Let's do that. Let's do that. You see, our condition is that real part of z of j omega equal to 0, which means that m1 m2 minus n1 n2 should be equal to 0. Isn't that right? If the real part is 0, then m1 m2 minus n1 n2 should be equal to 0. How can this be possible? Can m1 m2 be equal to n1 n2? Is that possible? Can m1 m2, I am asking a very trivial question, a common sense question, is this a possibility? No, because m1 m2 has a constant term, may have a constant term, n1 n2 cannot have a constant term. The minimum power in n1 n2 is s squared. No, odd multiplied by odd is even. But m1 m2 can have a constant term, n1 n2 cannot have a constant term, and therefore this is not a possibility. What is the way that this can be possible? Obviously there are, yes? We don't have any constants. Okay, then what are you talking of? Let's go back. m2 plus n2.
If constant term is 0, then m1 m2 is equal to m1.
Okay, if constant term is 0, then there is a factor of s in the numerator, there is a factor of s in the denominator. Okay, so
Out of the two, one M1 or M2 can one of them can have a 0 constant term.
out of the two I can, then there will be a difference in degrees. The 2 degrees cannot be equal then. You have a problem both ways.
So either the numerator has only odd or even and denominator has odd or even.
That is the only possible way. That is, I can have, there are two possibilities. I can have m1 equal to 0 and n2 equal to 0, or I can have m2 equal to 0.
Or M1 is equal to.
Why not both? Why not m1 equal to 0, n1 equal to 0? Then there is no function. Okay, so an LC driving point function, ZLC or YLC, must be of the form m by n or n by n. Agree? That is, it must be either purely even by odd or odd by even. In either case, it is an odd rational function. This is a great theorem. That is, the driving point, the DPI of an LC network is an odd rational function. Okay? If it is odd rational function, if the dpi is an odd rational function, what is the condition on m and n on their character, these two polynomials? It is a positive real function, isn't it? What can you say about m and n?
So they differ by 1.
They must differ by, can they differ by more than 1?
They cannot be.
Then it will not be PR. Anything else that you can say? Is M Hurwitz? Is M Hurwitz necessarily? Is the numerator Hurwitz?
Yes, sir.
Any positive real functions must have a numerator as well as a denominator which are both Hurwitz. Therefore, M and N are both Hurwitz. If M, a purely even polynomial, is Hurwitz, where are its roots? On the j omega axis. N, a purely odd polynomial. A purely odd polynomial is S times an even polynomial. Agree? It is Hurwitz. So its roots must also be all on the j omega. Origin included, yes. So we prove that LC driving point functions, all poles and zeros are on the j omega axis. The rest of the S function, rest of the S plane is banned as far as the poles and zeros are concerned. Okay, I state it again. The poles and zeros of an LC driving point function are all on the j omega axis. We will start from here next time.